Hello everyone, my name is Sergio Jiménez, a PhD candidate from Universidad Politécnica de Valencia, and today I'll be presenting to you my work titled Bilateral Blood-Brain Barrier Opening in Mice using Acoustic Holograms, which was carried out in collaboration with Columbia University. Currently, for non-invasive drug delivery into the central nervous system using focused ultrasound, the two approaches used are a single-element transducer and phased array systems. However, any of these allow the simultaneous generation of multiple focal spots into the brain, nor volumetric targeting of entire brain structures. However, we recently patented a technology using holographic acoustic lenses, as the ones you can see here, coupled to a single-element transducer, as sketched in this figure, showing great potential to solve these limitations, both generating simultaneous multifocal and arbitrary shapes targeting, as well as compensating the aberrations of the skull. In this work, we demonstrated for the first time a simultaneous bilateral BBB opening in mice using acoustic holograms in vivo, as sketched in this figure. The lens compensates the aberrations of the skull, the brain, and the coupling cone, and the bilateral BBB opening is achieved with a unique sonication and a unique injection of microbubbles, since it is a simultaneous targeting. The lens was designed using the pseudospectral simulation method implemented in the K-Wave toolbox for MATLAB, and the skull was obtained from micro-CT scan, and the brain volume was also included. Then we performed a backpropagation from the two virtual sources to the holographic plane placed in front of the transducer, recording here the complex holographic wavefront. Afterwards, we converted the complex conjugate of the holographic wavefront to height information by using the transmission coefficient expression of the Fabry-Perot resonator. Each pixel of the lens vibrates longitudinally, and the phase at the output of each pixel corresponds to the phase of each element of the holographic plane that we previously recorded. And finally, on the right, we have the 3D printed lens. If we step forward to the simulation results, in figure A, we can see the transcranial setup, showing in white contours the surface of the transducer, the surface of the lens, the coupling cone, and the skull, all of them surrounded by water. Subfigures B and C show the two distinct spots separated by 5.3 millimeters with a depth of field of 0.5 millimeters and a full width of half maximum of 0.6 millimeters. The two spots show a particular spherical shape because these lenses are able to encode all the reverberation and reflections inside the skull, becoming therefore a highly localized approach. Afterwards, we performed a unique sonication at 1.68 MHz with a unique injection of microbubbles, and by analyzing the post-treatment T1 MRI, we observed two symmetric spherical openings, as shown here by blue arrows, separated by 3 plus minus 0.7 millimeters. The discrepancy compared to the simulation was likely due to the differences between the skull scanned with micro-CT for designing the lens and the skulls of the treated mice. In conclusion, we demonstrated the first in vivo multifocal BBB opening in mice using a 3D printed holographic acoustic lens. Just a single sonication and a single microbubble injection were enough for the entire procedure. It is a highly localized technique for BBB opening, as these lenses can produce spherical spots by encoding all the reverberation and reflections inside the skull. In addition, this lens allows to control around 130,000 elements, about 2 orders of magnitude higher than phased arrays. So finally, the presented work demonstrates the feasibility of hologram-assisted BBB opening as a localized, time, and cost-efficient approach, which defines a new path for the complex requirements in the biomedical field. I want to acknowledge these funding sources that made this project possible, and also thanks to my research teams in Valencia and New York. Thank you for your attention.